So I would just like you to recall all the things that we have been doing. We will slowly start so that people will join. We have been talking about different aspects of chemical engineering. That's what we have been with respect to different processes. We discussed about that. Then we started talking about units. And then we have been talking about how to convert one set of units into another set of units. And we will today see some more such quantities whose units and converting from one unit to another unit we will discuss today. So hopefully people would have joined now. Yeah, more people have joined. Please keep a calculator ready. Please keep a pen, notebook ready. Take down notes while lecture is going on. We are going to do some more calculations today. In fact, from every class now we are going to do lots and lots of calculations. So you should be doing calculations parallelly rather than just listening to the lecture. This is not a theory subject, so it is very much an applied subject. So you need to be able to apply all the things that you are learning or that we are discussing in class. Okay, any doubts so far about what we were doing last time? Any quick questions? Please feel free to unmute yourself and ask questions. Are there any questions? Should we go ahead?
Yes, sir.
Okay, so the next quantity, any of your favorite quantity that you want to discuss now?
Pressure.
Pressure. So pressure we are going to talk a little bit more in detail. So the SI unit of pressure, everybody knows, it's Pascal. So Pascal is nothing but Newton per meter square, right? And then if we are talking about atmospheric pressure, then Pascal becomes a very small unit. So atmospheric pressure we talk um, uh, in terms of bar or in terms of atmospheres, right? Another unit, CGS unit, is dyne per centimeter square. Uh, Another unit that is very commonly used is, especially when we start talking about atmospheric pressures or pressure differences, is in terms of mmHg. So we say that 1 atmosphere is same as 760 mmHg. Why is that? We are talking about pressure, but we are actually talking about units of height here. So the reason we are doing that is, if you must have seen a barometer, that there is a mercury, and this mercury rises up in this tube, and it rises up to a level of 760 millimeters. That is the that is 1 atmosphere. So there is a complete vacuum here, right? So we talk in terms of actually not pressure, but we say in terms of height of a liquid column. So in this particular case, the liquid is that of is mercury. So if I say 760 millimeters of mercury, the height is what is this number telling us, 760, and the pressure that is arising out of this much amount of height, we can calculate in terms of h, the height, into rho, the density of the liquid, and g, at the static or hydrostatic head or hydrostatic pressure that corresponds to this height. So if you say 760, it is 0.76 meters. Rho for mercury is 13,600 kgs per meter cube, okay, and G is 9.81 meter per second square. So if you think about this unit now, kilogram meter per second square, that is newtons, okay, and meter cube in the denominator, that will give you Newton per meter square in the denominator. Right. So this 0.76 into 13,600 into 9.81, that is like 1.101396 pascals, and we say this is equal to 1 atmosphere. Right. So please feel free to stop me anytime. Please feel free to interrupt, and we can discuss any aspect. So another unit of pressure that we commonly use is pound per square inch, right? But pound is a unit of mass, so it is actually, when we say pound, it is what we actually mean is a unit of force corresponding to pound force. So it is denoted as lbf per inch square, or in short, it is written as PSI, pounds per square inch. Is it correct? So what we mean is actually pounds. The word force is something that people don't say or don't write. It is only written as pounds. But since we are talking about pressure, it is understood that it is pounds in terms of force. So just like we have units of pounds force, we could have units of kg force, right? So pressure, we could talk in terms of kg force per centimeter square as well. Right? So you can have any unit of force, and you can have any unit of length square. So centimeter square, meter square, inch square, all those units are possible. So if you are, let's say, tires in a car, they are inflated to a pressure of 30 psi, pounds per square inch. Can we convert this into, let's say, bar? Can you do this now? Convert 30 psi, which is same as, so 30 psi is same as 30 pound force per inch square. I would like you to convert this into bar. So just I'll give you a couple of minutes to do this. We would like to convert that into bar. So do this conversion, do this
The
calculation.
2.068 bar.
Okay, so one answer is 2.0. Put another color. One answer is 2.068 bar. Okay, any other answer? 2.06,
2.06.
same. Okay. Any other answer? So let's just try to see how to convert. So what we want is bar, which means what we want is, so before we convert to bar, we can convert to Newton per meter square, and then we know the conversion from Newton per meter square to bar. So what I want is Newton in the numerator instead of pound force, and meter square in the denominator instead of inch square. So let's do that slowly. So we have 30 pound force per inch square, right? Can we multiply something that will have units of kg force per pound force? Then this pound force would get cancelled.
Sir, 0.45, the one we were doing above.
Yeah, so let's
0.458.
yeah, so let's go slowly. uh, uh, Now we want, instead of inch square in the denominator, we want meter square in the denominator. So we need to multiply by quantity which has units of inch square and in the numerator and meter square in the denominator. So this inch square would get cancelled out. Then we would have this quantity in terms of kg force per meter square. Okay. But then kg force also we need to convert in terms of newtons. So we multiply by g. That's what we have seen last time, yesterday or last class. So then this would give, so this will be in terms of kg units of g if I take. So 9.81 if I take, it will be meter per second square. And then we don't have to write this kg force because now we have converted that kg into force. So now this will have units. Whatever is left now is units are kg meter per second square. So that is newtons, and this meter square in the denominator. Right. So what we need to do is now just multiply by a quantity. Let's not do into bar immediately. Let's go slowly. Newton per meter square. So if I take one, now it was kg force, right? We have multiplied by 9.81. That's how that force has got cancelled out. Okay, so if you take 1 pound force, that is the same as 0.454 kg force. That's what we were talking about last time. If you take 1 inch, if you take 1 inch, how many centimeters is that? So if you take 1 inch, it is 2.54 centimeters. So 1 inch is same as 0.0254 meters. But we need square, inch square and meter square. So we are going to square this. So then 30 psi would be equal to 30 into 0.454 into 9.81 divided by 0.0254 square. square. That will be so many Newton per meter square. Now we have got it in terms of Newton per meter square. I need to further convert that into bar, right? So what I need to do is I want bar, but I need to divide by Newton per meter square. So if I take 1 bar, that is equivalent to 10 raised to 5 Newton per meter square. Now then this Newton per meter square would cancel, and we would have answer in only what is left, the unit that is left now, that is bar, right? So our answer would be this whole thing. And if you do this, somebody do this, 20 into
Sir,
0.454. Yeah, go ahead.
207 099.3242.
Right. So this would, my God, who's that? Who's the one that is answering? Who was answering?
Yes, sir. 2.07.
Your name?
Arya.
Arya. So sorry, I still don't recognize your voices. So very good. Thank you, Arya. There is something that we need to discuss based on the answer that you have given. Right. Is there a point in writing to so many decimal places just because your calculator gives answer to so many decimal places?
No, sir.
No. So what you need to think about is what is the accuracy level that is required, and what is the accuracy level of our measuring instrument. What is the quantity that we are measuring? We are measuring PSI, right? We have measured, let's say, pressure in a tire, and that is 30 psi. Now what is the accuracy of the measurement of this 30 psi? Suppose we have gone to a petrol pump, filled tire, pressure in the tire, air in the tire, and the dial says 30 psi. So maybe this measured quantity 30 psi is only accurate up to, let's say, 0.2 psi. Maybe there is a dial pressure gauge that gives you up to accuracy level of 0.2 psi. So when you say 30 psi, it is actually 30 psi plus or minus 0.2 psi. Now if there is a digital indicator, then that digital indicator, if you have gone to petrol pump anytime, please do visit next time and see how they fill air in the tires. The digital has accuracy only up to plus or minus 1 psi, right?
Yes, sir.
So the level of accuracy is 1 psi in 30 psi. So that means our level of accuracy is at the most 3%, 3.33 if you like, just let's say 3. So there is no point in giving an answer which is more than having an accuracy level of plus or minus 3%. So even if you had just said 2.07 psi, or even if you had said 2.1 psi, how much error are we making? Our answer was 2.07 2.07 bar, not psi. Even if we had rounded it off to 2.1 bar, we would have made an error of 0.03 bar in a measurement of 2.07 bar, isn't it? So into 100 if you calculate, so error would be 0.03 divided by 2.07 into 100.
1% error.
Right.
1.4.
Yeah, it's about 1.45%. Let's just say 1.5%. Right. So the quantity that we are measuring is accurate up to plus or minus 3%. Even if you take a manual gauge, let's say the manual gauge is accurate up to 0.2 psi, then the error would be close to 0.3% or 0.5%. Right? Approximately, I'm just talking approximate number. And then we might write, instead of writing 2.1 bar, we might write 2.07 bar. Right? So that 0.09, so instead of 2.0709 dot, then our level of reporting the value has the same error of measurement as our original value, that we had original quantity in the original set of units that we had measured, right? So this is some point that I wanted to emphasize, and it is good that it has come about naturally by way of discussion. So be careful about what is the level of accuracy that our measuring instrument is measuring the quantity. Okay. So
So,
then, yes, please go ahead.
sir, can you repeat this point again about the level of accuracy?
Yeah, sure. So if I'm saying that if I'm measuring the pressure with a, let's say, a manual gauge or a dial, not an electronic or a digital indicator, that would have a level of accuracy of plus or minus 0.2 psi. So what, when we measure 30 psi, we are actually having a dial reading that is between 29.8 and 30.2, right? So the error is actually plus or minus 0.2 psi. So percentage error that we have made is 0.2 divided by 30 into 100. Let's just calculate that. How much is that? 0.2 divided by 30 into 100.
17% around.
17%.
1.7. 1.7. Sorry.
0.2 divided by 30. 0.2 divided by 30 into 100 is 0.67%, or let's just say 0.7%, or if you want 0.67%. That means there is no point in writing an answer which has more than 0.6% or 0.7% accuracy. So our answer that we had got was 30 into 0.454 into 9.81 divided by 0.0254 square divided by 10 raised to 5. So our answer was, based on what the calculator gave us, was 2.07093242 bar, right? So even if you had just rounded off to 2.07099, so even if you had said that this is the same as 2.071 bar, that would have still sufficed. Or even if I round it off further, I would have just simply said 2.07 bar. So the error that we have made in reporting the value is this difference, 2.071 minus 2.07. That means we have made an error in reporting of 0.001 bar. That error of 0.001 bar has been made in 2.071 bar. In terms of percentage accuracy or percentage error that we have made, it is 0.001 divided by 2.001 divided by 2.071 into 100. So this is 0.05%, 0.048 if you want. Okay. So this is actually much more accurate than this number, 0.67. Why is that? Because our measurement accuracy itself is only plus or minus 0.2 psi. So there's no point in writing an answer which is like this. Even if you have rounded it off to 2.07, that is still as good as accuracy that you have got when you say 30 plus or minus 0.2 psi. Okay, is that okay?
Yes, sir.
Okay. The next point when we talk about pressure is that there are two kinds of pressures we talk about. We talk about absolute pressure we talk about absolute pressure, and we talk about gauge pressure. Pressure that would be indicated by a pressure gauge. I'll just tell you the difference. Okay. So when I say absolute pressure, let's say imagine that I have a tank. Right? Now, let's say this tank consists of, let's say, pure hydrogen gas. Okay. Now, if I have to take out hydrogen gas from this tank, let's say the pressure of this gas is pressure of the hydrogen in this cylinder. I am measuring by a pressure gauge. Okay. So let's say this pressure gauge tells us that the actual pressure of the hydrogen gas in this tank is, let's say, 10 atmospheres. Now, if I have to use hydrogen from this gas, if I have to use the hydrogen gas from this cylinder, what will happen to this pressure? This pressure will keep on falling as I keep on using the hydrogen gas. So after some time, pressure will be 9 atmospheres. After some time, pressure will be 8 atmospheres. After some time, pressure will be 7 atmospheres, and so on. Do you agree?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Now I can keep on using this gas. Pressure becomes 6 atmospheres, pressure becomes 5 atmospheres, pressure becomes 4 atmospheres, pressure becomes 3 atmospheres, pressure becomes 2 atmospheres, pressure becomes 1 atmosphere, pressure becomes... Can I go below than 1 atmosphere?
No, sir.
No, sir.
No, sir.
No. Right? Why not? Because then the pressure that is inside the cylinder is equal to the atmospheric pressure. And then there is no pressure force that is responsible for getting the gas out of cylinder. There is no pressure difference between the pressure in the cylinder and pressure in the atmosphere outside. So then gas will not come out because pressure inside the cylinder and outside the cylinder, they are the same. So maximum amount that I can utilize from this cylinder is when pressure falls to 1 atmosphere. So there is no point in talking about pressure inside being 10 or 9 or 8 or 7 or 6 or 5 or 4. What we should actually be talking about is the pressure that is over and above atmospheric pressure. So when the actual pressure, when the absolute pressure is 10 atmosphere, the usable pressure is just 9 atmosphere. When the actual pressure or when the absolute pressure is 9 atmospheres, the usable pressure is actually 8. When the absolute is 8, the usable is actually 7, and so on. So when the actual pressure, absolute pressure is 1, the usable pressure is actually 0. And that's what we call as gauge pressure. Why? It is because what would have been indicated by a pressure gauge. So when you say pressure gauge, before you had attached this pressure gauge to the cylinder, you can Google how a pressure gauge looks like. What that pressure gauge would have measured is actually 0. So the scale starts from 0. The scale actually starts on a pressure gauge from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you will have a pointer. So even if the pressure gauge was not connected to the cylinder, it would have read 0. Why? Because not that absolute pressure is 0, but the pressure that is registered by the gauge is atmospheric pressure, because this pressure gauge is measuring the atmospheric pressure. because it is open to atmosphere, so air is there inside. So we talk about not the absolute pressure, but most of the time we talk about gauge pressure. What is the pressure over and above the absolute, okay, what is the pressure over and above the atmospheric pressure? So let's just take an example that will bring us to one more concept. Let's say there is a cylinder. Let's say this cylinder is 1 liter in capacity. 1 liter in capacity. When we say capacity, that means it has 1 liter volume. Let's say temperature is 273 Kelvin. And let's say pressure is 1 atmosphere absolute. Okay, can you visualize? There is a cylinder that has 1 liter volume, temperature is 273 Kelvin, and pressure is 1 atmosphere absolute. Can you tell me how many moles of gas are there inside the cylinder? Let's say there is a hydrogen cylinder. Or if you like, don't take 1, take
0.0447.
Correct. Okay. So, okay, instead of taking 1 liter, if you take, let's say, just make life simple, 22.414 liters. Now, can you tell me how many moles of gas are inside the cylinder?
One mole.
Yeah,
One mole.
Yeah, and
One
remember 1 mole. And remember what we have been talking about when we talk about moles. It is mole, but we are going to write it as gram moles. But is this 1 mole usable? Is this 1 gram mole usable?
No.
No, sir.
Because pressure is 1 atmosphere absolute. So I would rather say that pressure of the gas inside the cylinder is 0 atmosphere gauge, and we are going to denote that by G. G is not 9.81. G stands for gauge. So that means now what is usable is 0 moles. But what is actually inside is 1 gram. All right. So that's why we talk in terms of gauge pressure rather than absolute pressure. But if you have to refer to atmospheric pressure, let's say there is a cyclone that came yesterday, and if you saw in the cyclone, if you have seen local values of pressure at the eye of the cyclone, that was something like 985, 988, I think that was the lowest, 988 millibar. So here we are not talking about gauge pressure. Here we are talking about the absolute pressure. Right? So 988 millibar would mean 988 into 10 raised to minus 3. The word M, milli, suffix is 988 into 10 raised to minus 3 bar, which is same as 0.988 bar. Okay. Alright, so here we are talking about absolute pressure because we are talking about weather, we are talking about pressure of the air, local air pressure. But when we are talking about cylinders or when we are talking about equipment that are there in a plant, we would talk in terms of gauge pressure. All right. Okay, so the next important point that this brings us to, can you guess? What have we used?
Mole concept.
What have we used?
Gas laws.
Gas law, right? Mole concept we have already seen last lecture when we had converted these mass into moles. Okay. So we have automatically used gas laws. We have used ideal gas law. We have used R, universal gas constant. Right? What is the unit that we have used? We have used a unit. What is the unit?
Liter atmosphere per mole per Kelvin.
Right. So we have used liter atmosphere per mole. Again, it is gram mole. Gram mole. Kelvin. What is the value of gas constant in these set of units?
0.082.
Right. Now we can you convert this? So 0.082 liter atmosphere gram mole Kelvin. Can we convert this value into another set of units? Let's say joules per kilomole Kelvin. How would we do that? You may already know the value in joules per kilomole Kelvin, but I want you to go through the exercise of converting units from this set of unit to another set of units. I would need to multiply by 0.082. I would like to multiply. I would like to get rid of this gram mole in the denominator. I want kilomole in that place. So I need to multiply it by a quantity that will have units of gram mole per kilomole. Kelvin I want to keep as such. Liters atmospheres. I don't want liters. Joules is nothing but Newton per meter square and meter cube. So I want meter cube in the numerator. I want liters in the denominator. I don't want atmosphere. I want Newton per meter square. So I need to multiply by a quantity that will have units of Newton per meter square per atmosphere. So then this gram mole will cancel out. Liter will cancel out. Atmosphere would cancel out. And then we would have only kilomole in the denominator, meter cube in the numerator, Newton per meter square, and of course the Kelvin that remains. So that's what the unit that we want, joules per kilomole Kelvin. So if we take 1 kilomole, that is nothing but 1000 gram moles. If you take 1 meter cube, that is nothing but 1000 liters. If you take 1 atmosphere, that is nothing but 1.013 into 10 raised to 5 Newton per meter square. So our answer would be 0.082 into 1000 into 1.013 into 10 raised to 5 divided by 1000 Newton per meter square, meter cube, kilomole, Kelvin. Right? And Newton per meter square into meter cube, that is nothing but Newton into meter, that is same as joules. That's the unit that we want. So this 1000 just gets cancelled out. Straightforward, isn't it? Okay. So that's how we would convert this R into whatever set of units that we want. All right. Right. Next quantity. Any doubts so far?
No, sir.
If you have a doubt, please feel free to unmute yourself and ask. We have talked about pressure, we have talked about force. Yeah, just let's quickly talk about energy as well. It's a very important point that we are trying to say. Energy. So energy we could measure in terms of joules, calories, kilocalories. Any other unit that you are aware of?
Electron volt.
Ah, electron. Any other?
Erg.
Erg. Okay. Any other? Yikes. Ergs. Ergs and yikes sound similar. Never ever use this unless you are referring to some old, really old books. Any other?
Liter atmosphere.
Yeah, sure. Liter atmosphere. That's any volume and any pressure unit. Actually, it could be meter cube bar. It could be liter atmosphere. Any volume unit and any
Newton
pressure
meter.
unit. There is another unit that you may have heard, something called as BTU. Heard of this? Anytime? It's called as
No, sir.
British.
British thermal heat unit.
Yeah, British thermal unit.
Kilowatt hour.
Ah, very nice. Kilowatt hour. Unit of power and unit of time. Right? Right. So you will know the conversion, very straightforward. Calorie and joules. 1 calorie is
0.2.
1 calorie is how many joules? 0.2. Somebody said 0.2.
4.16.
4.18.
Yeah, 4.18 joules. So depending on what we are talking about, electron volt. So if you are not talking about the subject, you can mute your microphone so that there's no background noise. BTU. Anybody knows what one BTU is? One BTU. Praveen Kumar, you can mute your microphone. BTU, anybody knows? It's 252 calories. Anyway, we don't use BTU that often unless you are referring to some really old books. Okay, kilowatt hour. 1 kilowatt hour is how many joules?
3.6
10,
and 10 power 6.
10 power 3 upon
3.6 into 10 power 6.
Right, so one answer is 3.6 into 10 raised to 6. Anybody else? Right, we don't need to remember. We can just convert. 1 kilowatt hour is same as 1000 watt hours. We want joules, so we don't want hours there. We need to multiply by a quantity that we have seconds in the numerator and hours in the denominator. So if you say 1 hour, that is 3600 seconds, and watt is actually nothing but joules per second. So then this hour will get cancelled, second will get cancelled, and then we would have only joules left. So that is 3.6 into 10 raised to 6. So take care of how to convert one set of units into another set of units. The other thing that I wanted to mention is have you eaten any packaged food anytime? Anybody eats Lay's anytime, or any of these junk foods anytime? No, nobody eats.
yes sir.
Yes, sir.
Yes.
Yes, sir.
Yeah, we all eat. Very nice. So if you look at the food packaging, somewhere they will give nutritional information, and they will say that so and so food has say 250 calories, right? But they don't write C small, they write C actually capital. So that is just to make you feel not so guilty about eating the food. What it is actually not calories, it is actually 250 kilocalories, right? So they are just trying to write it as calories different from this calorie, so that you don't feel guilty about consuming so much amount of sugar or so much amount of food. So be careful about these packagings and read the label of these food packaging very carefully, right, before you eat. Okay, any other quantity that we would want to talk about? Otherwise, we'll go to the next concept, if you like. Any other quantity, any other doubt about converting units from one set of units to another set of units?
Power. Sir, power.
Okay, sure, power. That is the same, very nice, power. So any unit of energy and any unit of time. So SI unit would be joules per second, but we know that by a different unit, watts, in simply written as W, that's the accepted form. But you could have any other unit, kilocalorie per hour, you could have BTU per minute, you could
So
have
horsepower.
yeah, well, just coming to that, calories per second. And there is one other favorite unit that people use is horsepower. So 1 horsepower is how much for HP?
756.
746 watts.
746 watts, right? Just this. All these weird things have come about from essentially one country. Let's not name that country, but we all know which country has made our life difficult.
British.
Oh no, we are not going to blame anybody. There was Rankin somewhere, yeah, Rankin. All these problems came from there. They just didn't want to adopt that international system, SI units. Okay, any other point, or shall we go to the next next important point, compositions? Maybe I'll just give you an example, just give you some homework. So specific heat. So specific heat has units of how much energy is required per unit mass, per unit rise in temperature, or per unit change in temperature. So let's say specific heat of water, for example, or let's take some substance for that matter. So SI unit, this is your SI unit. Okay. But that's not the very commonly used unit that we use. We use some other unit that is very common for specific heat. Let's say specific heat of water. So specific heat, as you know, is indicated by the word Cp or a symbol Cp. So let's say Cp of water is, let's say, 1 kilocalories per kg Kelvin. What I would like you to do is convert this into, let's say, joules per kg per degree centigrade. Remember, this per degree centigrade or per degree Kelvin is the change of temperature. It is the amount of energy required to change the temperature by 1 Kelvin for 1 kilogram mass. So, okay, another thing I would like you to convert is 1 kilocalories per kg Kelvin. I would like you to convert into another set of unit, let's say BTU per pound per degree Fahrenheit. Okay? Specific heat of water. So convert this, that's your homework. And you can always check your answer with Google, specific heat of water. Another small homework I can give you is, let's say, thermal conductivity. Thermal conductivity has units of watt. Units of thermal conductivity, anybody knows? Thermal conductivity. Anybody heard of?
Watt per unit length.
Yeah, meter Kelvin, SI unit if you like. SI unit. So again, this Kelvin that is there in the denominator, it is the gradient of temperature difference between the two ends of a rod, if you like, and the rate at which heat is converted or transferred from one end of the rod to another end of the rod. So, okay, so suppose, let's say, thermal conductivity of water is about 0.6 watt per meter Kelvin. I would like you to convert that into, let's say, kilocalories per hour per feet per degree Fahrenheit, or why kilocalories? Let's make it BTU. BTU per hour per feet per BTU per hour per feet per degree Fahrenheit. Remember, again, this per degree Fahrenheit is the change in temperature or a temperature difference which is causing that transfer of heat from one location to another location. Okay, so that's your homework. Do that and you can check your answers with Google. Okay, compositions. Want a break of 5 minutes or can we continue? Break of 5 minutes or should we continue? Somebody say something.
So you can
Sir, we
continue.
may continue.
We can continue. Yeah.
You can continue.
Okay. So composition. So we are talking about, many times we talk about mixture of compounds, or we talk about solutions. So if you are talking about solutions, what are the common ways of writing compositions? So for example, we may be talking about HCl solution. How do we represent the composition of that solution?
Concentration in terms of molarity.
Right. So we talk in terms of concentration that is there, or moles that are there per unit volume of the solution. So we talk in terms of molarity, or if we are doing titration, we are interested in how many H plus ions or how many H plus ion equivalents are there that can be neutralized. So we talk about normality. Okay.
Molarity.
Yeah.
If,
So yes.
if
So
temperature is affecting the concentration.
yes, so if temperature, so what we rather talk about is, so when this molarity is there, it is in terms of how many gram moles are present per liter of solution. Okay. So this volume can change with respect to temperature, and therefore it is we need to specify what temperature we are measuring and so on. So another way we represent is in terms of molality. Molality. That is how many gram moles are dissolved per kg of solvent.
Solvent.
It is not per kg of solution, it is per kg of solvent. Okay. So that's how we talk, especially when you start talking about osmotic pressure. These are the kinds of molality is very commonly used unit for talking in terms of for when we talk about osmotic pressures, right? Many times when we have mixture of compounds, okay, so we talk on the basis of percentage of compound in the mixture. So for example, we may have a mixture of ethanol and water. So we will talk about how much percentage of ethanol is there in the mixture, and then that percentage we can define in terms of different quantities, percentage of different quantities. So for example, we can talk about percentage by weight. So which means if I take 100 grams of mixture, and if that 100 grams of mixture contains, let's say, 30 grams of ethanol and 70 grams of water, in terms of percentage by weight, it will be 30% by weight is ethanol in that mixture. Or that percentage we can talk in terms of percentage by moles. So if I take 100 gram moles of mixture, and let's say that 100 gram moles of the mixture has, let's say, 17 grams of ethanol and 83 grams of water, this mixture we would say has 17% by moles of ethanol. So we have defined percentage on the basis of mass or weight, or we have defined percentage in terms of moles. Okay. Sometimes we would write, let's say, air contains, let's say, oxygen and nitrogen. So here we talk either in terms of percentage by moles or percentage by volume. So they are the same. Why? Because moles and volume are interrelated by ideal gas law, and it is the same conversion factor between volume and moles that is applicable to nitrogen as well as to oxygen. So if I say air contains 21% volume percent oxygen, 79 volume percent nitrogen, that is the same as 21 mole percent oxygen and 79 mole percent nitrogen. Why? Because volume, if I take, let's say, 100 liters of solution, if I take 100 liters of air, of solution, now we have air, it's a solution of gases, we have 21 liters of oxygen, we have 79 liters of nitrogen. If I convert this into moles of oxygen, I would have to use ideal gas law. If I convert this into gram moles of nitrogen, oxygen, and gram moles of nitrogen, I have to use ideal gas law, and converting volume into moles, it is the same ideal gas law that is applicable, and therefore the mole percent and volume percent are identical when we are talking about gases. But when we are talking about liquids, we would not talk in terms of volume percent. Never ever. Why? Because if we take, let's say, for liquids, if we take, let's say, 30 liters of ethanol and 70 liters of water, and we mix them together, we will not get 100 liters of mixture. Why is that?
Because
interaction between the molecules.
Correct. Interaction between molecules. There is a reason these molecules interact with each other, hydrogen bonding, and therefore volumes are not additive volumes are not additive, not additive. It may become 98, it may become 99, right, depending on temperature and all other conditions, right? So therefore we don't talk about volume percent when we talk about liquids, but in a gas volumes are additive. If I take 30 liters of oxygen and I mix 25 liters of carbon dioxide, I will get 55 liters of oxygen carbon dioxide mixture, right? Molecules are not interacting, they are ideal, so there is no interaction. And you will see later on in your semester 3 that even that breaks down for gases under high pressures. And that will come in thermodynamics. Let's not do that just now. Let's to illustrate all these concepts, let us take a problem, and you are going to do this problem for yourself, and then we will talk about. So let's say we have a acetic acid solution. When I say solution, it is an aqueous solution. That means we have acetic acid and water, right? So let's say in this solution, acetic acid is let's say 10% by weight. Okay, let's say density of this solution is, let's say, 1 gram per centimeter cube. Let's make life simple. I would like you to calculate the following. One, composition of this solution in terms of mole percent. That is the first thing that I would like you to calculate. Second thing I would like you to calculate is I would like you to calculate the composition of this mixture of this solution in terms of molarity of acetic acid. Third thing I would like you to calculate is composition in terms of molality of acetic acid. Okay, let's do this problem in the next 5 to 6 minutes, and then we will see the solution. So please do this problem, solve it by yourself, then we will see the solution after some time.
Sure.
Yeah,
So we could assume the volume.
you can do whatever you like. Whatever method you want to apply. Just tell me the answer. How to do it is your problem. You just have to solve by whatever tricks that are available to you at your head. There's an important point that is coming. That's why I want you to do this problem. Once you're done, just tell me your answers. Any one you have done, tell me the answer. Don't wait for
So
all three.
mole percentage is 3.22.
Okay.
Yes, sir. 3.2.
The molality is 1.667.
Molality or molarity?
Molality
Molality is
1.667.
1.66. Okay.
The molality is 1.85.
Molarity
Molality is 1.85.
1.8.
1.
Two answers.
Molarity is 1.67.
Yes, sir.
Molarity.
Molarity is 1.67.
Yes, 1.67. 1.85 is a molality.
Yes, sir.
Answer for mole percent.
So 3.22.
Okay. One more answer.
The mole percent
Yeah, mole percent. Word.
3.33, sir.
3.63.
33.
3.6 did you say?
33.
3.33.
Yes.
Yes, sir. 3.33.
So for molarity it's 1.67 and for molality it is 1.85.
Any other answer?
So for molality, it is 1.85.
Okay. If 1.85 seems to be popular, I don't know if it is correct or not.
Mole percent is 3.33.
3.33. Okay, so stop whatever you are doing. Stop whatever you are doing. There is an important point. That's why we need to discuss. You need to pay attention. Even if you have completed, it's okay. Even if you have not completed, it's okay. Even if you have got the answer, it's okay. Even if you have not got the answer, it is okay. Even if your answer is correct, it is okay. Even if your answer is wrong, it is okay. We are trying to see how to solve. And that brings us to one very important concept. Suppose I want to convert this. I have a 10% by weight solution. I want to convert to mole percent. That means this weight I need to convert, or mass I need to convert to moles. So I would need molecular weight. Right? So suppose we take 100 grams of this mixture or 100 grams of this solution. Out of this 100 gram, we would have 10 grams of acetic acid because it is a 10% by weight solution and 90 grams of water. Okay. Now we need to convert to moles. So 10 grams of acetic acid, molecular weight of acetic acid. Acetic acid is CH3COOH. Molecular weight is 60. Water, molecular weight is 18. So 10 grams of acetic acid correspond to 10 divided by 60, which is 1/6. This is 0.167 gram moles. 90 grams of water would be 90 divided by 18, which would be 5 gram moles of water. So this mixture, which we have considered for our purpose of calculation, we have taken 100 grams of this mixture, 100 grams of this solution. This mixture is going to contain 5.167 gram moles. That 5.167 gram moles is coming. Why it is coming? It is 0.167 gram moles of acetic acid and 5 gram moles of water. Total is going to be 5.167 gram moles. So what is the mole percent? For acetic acid, it is 0.167 divided by 5.167. That is the mole fraction, if you like. Mole as a percentage would be 0.167 divided by 5.167 into 100. So 0.167 divided by 5.167 into 100. That's nothing but 3.23%. And mole fraction of water would be 5 divided by 5.167. Mole percent of water would be 5 divided by 5.167 into 100. It is 96.77%. Okay. So mole percent of acetic acid in the mixture is 3.23%. Mole percent of water in the mixture is 96.77%. Right? So this is right. Okay. Now, what is the molality and what is the molarity? Let's do molality first. Molality. How many gram moles of acetic acid is there? Gram moles of acetic acid per kg of water solvent. Okay. How many gram moles of acetic acid do we have? We have 0.167 gram moles. 0.167 gram moles are in how many kgs of water? It is in 90 grams of water. 90 grams of water means it is 90 divided by 1000, 0.09 kgs of water. So molality would be 0.167 divided by 0.09 gram moles per kg. 0.167 divided by 0.09. That is nothing but 1.86. Right. Now, molarity. Molarity is gram moles of acetic acid per liter of solution. Per liter of solution. How many gram moles of acetic acid are there? 0.167 gram moles are there. How many liters of solution are there? I have 100 grams considered. I have considered 100 grams of this solution. 100 grams of the solution, and density is 1 gram per cc.
0.1 liter.
Right. That means it is same as 100 centimeter cube of solution. 100 centimeter cube of solution is same as 100 ml of solution, milliliters, which is same as 0.1 liters of solution. Okay. So 0.167 gram moles are present in 0.1 liters of solution. Okay. So molarity is 0.167 divided by 0.1, that is 1.67 gram moles per liter of solution. It is 1.67 m molar. Okay. Let's take one more problem. Or let's take two more problems just to be. Let's take one problem. So let's say we have okay. Let's say we have 2 molar H2SO4 solution. Let's say density of this solution is say 1300 kgs. 1300 maybe too much. 1100 kgs per meter cube. I would like you to calculate weight percent of H2SO4 in the solution. Okay. Do this problem. So another 4-5 minutes. Let's do the problem.
So 17.818%.
Okay. 17.82. That's one answer. Let us
Yes,
read.
17.818. So 17.82.
Yeah, okay.
Yes, sir. I also got the same.
Yes, sir. 17.818.
Okay.
Yes, sir. 17.81.
So 17.81.
It's a 17.81.
Seems to be very popular answer. Okay.
So I am getting as 0.0178.
0.0178. All right.
Yes, sir. 0.0178.
All right. You are telling me mole fraction or mole percent? Sorry, weight percent or weight fraction?
Weight percent.
Weight percent, right? Okay. So 2 with 0.0178.
Yes, sir. 17.82.
Yes, sir. 17.82.
Okay.
Yes, sir. 17.82.
Yes, sir. 17.82.
Perhaps these people are right, everybody else is wrong. perhaps both answers are wrong. Obviously, both answers cannot be correct.
Sir, 0.178.
Now that answer is gaining popularity.
1.88, sir.
Oh, another answer, 1.88.
0.178.
Oh, still one more answer, 0.17. Yeah, please tell answers. We have only got how many? 10, 12, 15, 17 answers. There are 90 people in the class.
Sir, the second one.
Okay.
Sir, 17.82.
Okay.
Sir, first one.
Okay. Other people?
Yes, sir. The first one, sir.
Sir, first one.
Okay. Okay, let's try to see the solution. We need to convert molarity. That means there is something about how many moles are dissolved in how many liters of solution. Suppose, can we take, let's say, suppose we consider one meter cube of solution. If I take 1 meter cube of solution, if I take 1 meter cube of solution, what would be the weight or what would be the mass of that solution? It would be 1100 kgs. Why? Because the density of the solution is 1100 kgs per meter. Now, this 1 meter cube of solution, that means it is 1000 liters of solution. How many gram moles of H2SO4 would be there? It would be 2000 gram moles of H2SO4. Why? Because the molarity is 2. 1000 into 2 will give you 2000 gram moles. 2000 gram moles of H2SO4 is same as 2 kilomoles of H2SO4. So I have 1000 kgs of solution. Sorry, I have 1100 kgs of solution. In that 1100 kgs of solution, I have 2 kilomoles of H2SO4. What would be the mass of that 2 kilomoles of H2SO4? I need molecular weight of H2SO4. Molecular weight of H2SO4 is 98. So 2 kilomoles of H2SO4 would be 2 multiplied by 98, which is 196 kilograms of H2SO4. So when I take 1 meter cube of solution, that means I have 1100 kilograms of solution. That 1100 kilograms of solution are going to contain two things. It is going to contain H2SO4 and it is going to contain water. H2SO4 is 196 kilograms. Water would be 1100 minus 196 kilograms. That is 904 kgs of water. So 1100 kilograms of solution is going to contain 196 kilograms of H2SO4. It is going to contain 904 kgs of water. What is the weight fraction of H2SO4? weight fraction of H2SO4 is 196 divided by 1100. What is the weight percent of H2SO4? Multiply that by 100. So 196 divided by 1100 into 100, that would be 17.82%. Okay. So all those who got this answer 0.0178, 1.88, 0.178, check what is the mistake that you have made. You check for yourself and then don't need to tell us. Okay, so the important point or important concept. Now can you tell me what is the important concept? What is the common theme or common thing between these two problems?
Density is given and you have to calculate volume and mass.
Density is given, okay, that is a that is there, but yes. Anything else that is common?
We assumed mixture.
Yes. What is common is in the first problem, we assumed that we are doing calculations for this 100 gram of solution. In the second problem, we assumed that we have 1 meter cube of solution. So when we are calculating something, we need to assume some quantity as a start point for solution. In the first problem, for solving. In the first problem, our starting point was 100 grams of the solution. In our second problem, it was 1 meter cube of solution. Okay. This some quantity that we assume, we need to give a nice name for this sentence. We need to give a short name for this sentence, or we need to shorten this sentence. Otherwise, anybody could understand. Even the 12th standard kids can understand what we are talking about. We need to tell them, we need to tell your juniors that we are doing some hi-fi things. Isn't it? You need to impress upon your juniors that you are doing hi-fi things. So if you say this sentence to your juniors, they will say, ah, we also know this. So we use a little bit of jargon just to impress people. We call this as basis for our solution. Okay? And irrespective of the basis that you take, your answers will not change. Right? So that's the important concept. So let's do this problem. Let's do the second problem. With another basis. Let's assume that our basis is, let's say, 1 kilogram of solution. Suppose that is our basis. Right? So if it is 1 kilogram of our solution, we know the molarity. We need to convert this into volume. Right? So what is the density? It is 1100 kilograms per meter cube. This is same as 1.1 kilograms per liter, isn't it? So if I take 1 kilogram of solution, what would be the volume of that solution? It would be 1 divided by 1.1. So this would be 1 divided by 1.1. This would be 0.909 liters of solution. Now molarity is 2 moles, 2 molar, 2 molar. That is the molarity of the solution. That means this 0.909 liters of solution, moles or gram moles of H2SO4 would be 0.909 multiplied by 2. That would be 1.818 gram moles of H2SO4. We want weight percent. We want weight percent. Right? So 1.818 gram moles of the H2SO4. What would be the mass? What would be the weight? Grams of H2SO4? That would be 1.818 into 98. This would be 178.18, 178.2 grams. 178.2 grams are there in how much mass of the mixture? 1 kilogram of the mixture, 1 kilogram of the solution, which is same as 1000 grams of solution. Right? So what is the weight fraction? Weight fraction of H2SO4 would be 178.2 divided by 1000. What would be the weight percent? This multiplied by 100, which is 17.82%. Same answer. So the important concept is basis. Okay, let's take another problem. Imagine that I have, let's say, okay. Let's say I have a phenol water mixture. So in the phenol water mixture, we have, let's say, this contains how much? Let's take 0.05 mole percent phenol, and therefore 99.95 mole percent water. Can you convert this into weight percent? That is one. Second thing I want you to convert is into grams of phenol or milligrams of phenol per liter of solution. Let's assume that density is just pure water essentially. So density is 1 gram per centimeter cube, which is the same as 1000 kgs per meter cube, which is same as 1 kg per liter. They are the same. Essentially pure water, very small amounts of phenol. Okay, I would like you to convert it into weight percent. What is the weight percent of phenol? And how many milligrams of phenol are present per liter of solution? Instead of gram moles, is grams per liter. That's one more way of representing composition. Okay, let's do this in the next 5 minutes and then we will see a solution. now you should be able to do this very fast.
So, sir.
Sir,
Yeah.
first is 0.26%.
Yes, sir.
So 0.26%.
Yes, sir. 0.26%.
Yes. And second one said 2.60.
Which one?
Second
What
one,
were you
2.
saying?
0.261%.
Yeah, 0.26. Atharva, you are saying something else?
No, 2.609.
2.609.
609.
So 6 1.
Second one. Excuse me, sir.
Yeah.
Answer of second one, sir.
Oh, it is not this answer. It is this answer.
Sir, for weight percent of phenol, it is 0.26.
Okay.
Yes, sir. 0.26.
Yes,
For weight
it
Yes,
percent,
sir.
it is
Point.
0.26.
Yeah, that seems to be very popular. Second one, milligrams of phenol per liter of solution.
2.61.
2.6. We'll just wait for other people. Some more people.
Yes, sir. First one is 0.26.
Yeah.
Yes, sir. 0.26 for weight percent, and milligrams of phenol per liter solution is 2.61.
So second answer is 2.61.
Yeah,
Yes, sir. It
2.6.
is 2.61.
So second one is 2.
Okay, let's try to solve. Let's just try to see the answer, just so that everybody can do, and even if they have problems, they can, their questions or their doubts will get answered. Okay, so we have moles, mole percent. We want weight percent, or we want milligrams, so we want mass. So we need molecular weights. Molecular weight of phenol, C6H5OH. What is the molecular weight?
94.
94. Water, of course, 18. So now, if I take basis as, let's say, 100 gram moles of mixture, this 100 gram moles will contain 0.05 gram moles phenol and 99.95 gram moles water. So 0.05 gram moles of phenol would be 0.05 into 94 grams of phenol. 99.95 gram moles of water would be 99.95 multiplied by 18 grams of water. The total mixture would be 0.05 multiplied by 94 plus 99.95 into 18. This will be the total grams of the mixture. So weight percent or weight fraction of phenol would be 0.05 into 94 divided by 0.05 into 94 plus 99.95 into 18. And weight percent phenol would be this multiplied by 100. Okay, and I don't know how much we are getting, so 0.05 into 94. We just do so that we're absolutely sure about the correct answer. So 0.26 weight% phenol. Okay, now milligrams per liter. Okay. Now if you want, I can take another basis. Basis is 1 liter of solution. 1 liter of solution is same as 1000 grams of solution. Density I know, 1 kilogram of solution. Density is 1 kilogram per liter, 1000 kilogram per meter cube, 1 gram per cc, whatever you like. So 1 liter of solution, oops, 1 liter of solution is same as 1000 grams of solution. And 1000 grams of solution, we know that weight% is 0.26 weight%. So that means it is 0.26 weight, 26 grams per 100 grams. And in 1000 grams, it would be 0.26 into 1000 divided by 100. That is nothing but 2.6 grams. So 0.26 is the weight%, the fraction, divided by 100. 0.26 divided by 100 is the fraction into 1000. So it will be 2.6 grams of phenol. And it will be 1000 minus 2.6 grams of water. Okay. So in terms of milligrams, it will be 2.6 into 1000, which is 2600 milligrams of phenol. So what do I want? Milligrams per liter. So this would be 2600 milligrams of phenol per liter of solution, because my basis was 1 liter. So this answer is wrong. All right. So perhaps you were telling me grams per liter. I did not ask you grams per liter. I am asking you milligrams per liter. Do you agree?
Yes. Yes, sir.
Yes, sir.
Okay. Another concept, another important point is sometimes when we are dealing with such small quantities, 0.05 mole% is a very small quantity of phenol, or 0.26%, very small quantity of phenol. So rather than talking about percentage, we talk about another way of representing the composition. See, we have 0.05 mole% phenol, 0.05 mole% phenol, or we have 0.26 weight% phenol. That means if I take 100 gram moles or 100 moles of mixture, 0.05 moles of phenol are present, isn't it? Or if I take 100 grams of mixture, 0.26 grams of phenol are present. So these are very small quantities. Right? And then somebody may make an error in understanding, somebody may make an error in writing, somebody may make an error in hearing. So rather than talking about 100 moles of the mixture, what if we talk about moles of mixture? Do you like this quantity? We are talking about 10 raised to 6 moles of mixture or a million moles of mixture. How many moles of phenol would be present in a million moles of the mixture?
50.
It would be 0.05 moles are present for 100 moles. In a million moles, it would be 0.05 divided by 100 into 10 raised to 6. So that is 0.05 into 10 raised to 4, which is same as 500 moles. Right? So rather than talking about composition in terms of mole percent, we would rather talk about 500 moles of phenol are there in 1 million moles. Right? So we talk about parts per million. So we have 500 parts per million moles, right? Or 500 ppm by moles. So 500 is a nice sizable number to communicate rather than 0.05. Okay? Or let's look at it this way. Instead of 100 grams of the mixture, suppose I take million grams of mixture. How much phenol would be there in million grams of mixture? 0.26 divided by 100 into 10 raised to 6. This would be 0.26 into 10 raised to 4. This would be 2600 grams of phenol. So phenol, we can say, is 2600 grams per million grams. Or in the mixture, I have 2600 parts per million by weight. Right? Or we can say 2600 ppm by weight. You see, so the ppm by weight and ppm by moles, they are different. Right? The third thing, 2000 milligrams per liter. This is like 2600 2600 2600 milligrams per liter. Right? So that is same as milligrams. That is something similar, 2600 ppm by weight. Why? Because our density is 1 grams per cc. So this is same as 2600 milligrams per 1000 ml, if you like, or 1000 grams. Isn't it? That's why you get into same 2600 ppm by weight. ppm by weight and milligrams per liter, they are the same, they are identical, because the density is 1 gram per ml or 1000 kgs per meter cube. It is basically water. So if it's a dilute aqueous solution, density is nearly that of water. Which is 1000 kgs per meter cube or 1 kg per liter, 1000 gram per liter, whatever your favorite units you like, 1 gram per ml, 1 gram per cc. Then ppm by weight and ppm by and milligrams per liter, they are the same. Okay. All right, any doubts so far? Anything I need to repeat? Anything we need to discuss again? Can we go forward?
Yes, sir.
What concepts have we learned today? We are coming to the end of the day. Tell me, what concepts have we learned today? What concepts have you learned today?
Selecting a basis for calculation.
Basis. Very important to select the basis. You can take any basis you like, but do calculations which are consistent with the basis. Second thing that we have learned is converting units from one set of unit to another.
Compositions.
Right, compositions. What are the different ways in which we write compositions? Okay, anything else that we have learned today?
Error.
Say that again.
Error. The
Yeah, okay.
figures.
Error, accuracy, significant digits. You should not be writing answers with very large number of digits just because our calculator gives so. We will always round off depending on what is the error associated with that measurement. We are talking about measuring the distance of something with a ruler, and we say something has 5 centimeter length. Error that we are making is in, depending on your ruler of course, but if your ruler is nice, error is 1 millimeter. So we are making an error of 1 millimeter or 0.1 centimeter in 5 centimeters. So that's how we will round off our values that we report. Any other point that we learned? We learned very important, 1 or 2 very important points. Couple of more points we have learned which you have forgotten. Let me take you back to that sheet. Do you see any other point that we have learned?
Sir, absolute and constant pressure.
Right. Very important. Absolute pressure. Gauge pressure. So gauge pressure we will just denote by suffix G standing for gauge. Another important point that we learned today, using ideal gas law. Units of R. Right? Any other thing that we learned today? Of course, homework is there. I gave you this homework, converting units for specific heat. and thermal conductivity. These two homework problems are there. Do them. Okay. Second, I would like you to revise concepts of pH and pKa. So dissociation constants. Did you learn these things in your 12th standard?
Yes, sir.
Yes, sir.
So when we say pH, what we mean is pH is minus log to the base 10 H plus ion concentration. Okay. pKa, suppose we have acetic acid. We know that acetic acid dissociates as acetate ion and H plus ion. So if we write the equilibrium constant for dissociation of acetic acid would be the acetate ion concentration, the H plus ion concentration divided by the undissociated acetic acid concentration, and pKa would be minus log to the base 10 Ka. Right? Just so that you revise properly, I am going to ask you two problems. Suppose I have dissolved 60 grams of acetic acid and made a solution from that. What would be the pH of this solution? Second is, suppose we have acetic acid solution and we add sodium hydroxide to that and we make pH equal to, let's say, 4. We adjust the pH to pH 4. What would be the percentage dissociation of acetic acid? So do these two problems just so that automatically you will be able to revise your concepts of pH, pKa and so on. Okay. You can refer to your 12th standard books, internet, whatever you want to refer to, you can refer to, but solve these two problems. Next class on Tuesday, what we will start doing is applying all these principles that we have seen today to doing calculations for different processes. All right. Shall we stop here for the day? Any other doubt? Anything we need to discuss? Let me stop recording.